Module 10, Lecture B, Performance and Debug. By the end of this lecture, you will be able to enable and configure mixed precision training in TensorFlow 2.20.0 to leverage modern GPUs and TPUs. Use TensorFlow profiling tools to identify performance bottlenecks in models and input pipelines. And diagnose and mitigate common numerical and stability issues such as NaNs and exploding gradients. Mixed Precision Setup. Global Mixed Precision Policy. A global mixed precision policy is a single setting that tells a deep learning framework what floating point precision to use throughout a model. Instead of choosing precision for each layer, you define this policy once, and it controls the default data type for computations. This lets most operations run in lower precision while keeping important values like weights in higher precision. It is especially useful in large projects because it enforces a consistent numerical strategy across contributors and makes it easy to change precision settings without rewriting model code. Modern GPUs and TPUs are built to run low-precision arithmetic very efficiently, especially half-precision operations. By setting a global mixed precision policy, you let the framework automatically use lower precision where it is safe and higher precision where accuracy is critical. For example, in medical image analysis, convolutions can run in lower precision for speed, while parameters stay in higher precision to avoid numerical errors. This global setting removes the need to tune each layer by hand, but still allows you to adjust specific layers when necessary to balance performance and stability. Using a global mixed precision policy treats numerical precision as a core training setting, much like choosing an optimizer. This makes it easier to document, share, and compare experiments, since each setup clearly states which precision policy it uses. Teams can define different configurations for different training stages, matching precision choices to their hardware and risk tolerance. As new accelerators appear, they can evaluate how these policies affect performance and model quality without changing the model's architecture. In this way, the precision policy connects the model's design to efficient execution on modern hardware. Python code, Global Mixed Precision Policy. This short script demonstrates how to use a global mixed precision policy in TensorFlow. It relies on a very small model, so the example runs quickly and is easy to follow. To try it yourself, run the script in Google Colab with TensorFlow version 2.20.0 installed. This command installs TensorFlow version 2.20.0 to make sure that exact version is available in your environment. Using a specific version is important for compatibility with the script you are running. It helps avoid issues that can occur when features, such as mixed precision support, change between TensorFlow versions. We begin by importing 3 key libraries. The operating system library lets our program interact with the computer's operating system. The random library gives us tools to generate random numbers and perform random operations. Finally, we import NumPy, a numerical computing library that helps us work efficiently with arrays and perform mathematical calculations. We begin by importing TensorFlow, which we use to build and train our machine learning models. Then we import Keras, the high-level interface within TensorFlow that makes creating neural networks easier. Finally, we bring in the Keras layers module, which provides components like convolutional and dense layers used to define the structure of our network. Together, these imports prepare all the essential tools needed to design and train the neural network in the rest of the script. We start by setting a seed value of 42 to make all random operations reproducible. This means that every time the code runs, it will generate the same random results. We set the seed for Python's random number generator, then for NumPy's generator, and finally for TensorFlow's generator. Doing this ensures that any randomness in data handling or in TensorFlow operations, such as initializing neural network weights, stays consistent across runs. The script first reports the version of TensorFlow in use to confirm that the environment is set up correctly and that the code is compatible. It then checks for available graphics processing units by listing physical devices of type GPU. This step is important because having a GPU can greatly improve the speed of training and running deep learning models. This code imports the mixed precision utilities from TensorFlow Keras to enable mixed precision training, which can speed up models by using lower precision data types when appropriate. It then defines a list of available precision policies, including standard single precision and a mixed float 16 policy. Finally, it prints these policies so you can quickly confirm that the mixed precision API is available and ready to use in your model. We start by creating a mixed precision policy in TensorFlow that uses mixed float 16, which combines 16-bit and 32-bit floating point numbers to improve performance on supported hardware. We then set this as the global policy, so it automatically applies to all layers and models created afterward. Finally, we print the current global policy to confirm it is active, ensuring the model will use mixed precision during training. The code first loads the MNIST handwritten digit dataset using Keras, then selects the first 2048 images to keep the example small and fast. It converts the image data to floating point numbers and normalizes the pixel values by dividing by 255 so they fall between 0 and 1, which helps the model train more effectively. It also extracts the corresponding labels for these samples and converts them to integers, making them suitable for use in a classification model. To prepare image data for convolutional layers, we need to add a channel dimension to the training set. We do this by expanding the array so that a new dimension is added at the end, turning each image from 28 by 28 into 28 by 28 by 1. The extra dimension indicates that each image has a single channel, which is standard for grayscale images. After this transformation, we check the shape of the training data to confirm that the new channel dimension has been added correctly. Before building the model, the code checks that the training data has the correct shape and format. It confirms that each image is 28 by 28 pixels with a single channel, as expected for grayscale input to the model. It also verifies that the labels form a one-dimensional array suitable for training. These checks help catch data preprocessing errors early and prevent problems during model training. We build a simple convolutional neural network for MNIST by first defining an input layer for 28 by 28 grayscale images. We add a two-dimensional convolutional layer with 16 filters of size 3 by 3 and use the ReLU activation function. A max pooling layer then reduces the spatial size of the feature maps, and we flatten the result into a one-dimensional vector. This feeds into a dense layer with 32 units and ReLU activation to learn more complex patterns. Finally, an output dense layer with 10 units produces predictions for the 10 MNIST classes, completing the model under the previously set global mixed precision policy. To see how the global mixed precision policy affects a model, we inspect the data type of each layer. We loop through the model's layers and print each layer's name along with its data type. This lets us confirm that the mixed precision setting has been applied as intended. In this case, we are checking that computations are using mixed float 16 precision throughout the model. We start by creating an atom optimizer with a learning rate of 0.001 as the base for training. Then we wrap this optimizer with TensorFlow's mixed precision loss scale optimizer. This wrapper is important when using mixed precision because it maintains numerical stability. It does so by dynamically adjusting the loss scale to help prevent underflow during training. The model is now being compiled, which prepares it for training. It uses a loss scale optimizer to keep calculations stable when using mixed precision. The loss function is sparse categorical cross-entropy, which is appropriate for classification problems with integer class labels and works directly with raw, unnormalized outputs from the model. During training, the model will track accuracy as a metric, so we can monitor how well it is performing. The model is trained using a fit function that takes the training data and labels and runs for one full pass through the dataset, known as one epoch. It uses a batch size of 64, meaning it updates its weights after processing 64 samples at a time. The training output is silenced by setting the verbosity to 0, so no progress messages are shown. This quiet single epoch setup is useful for quick demonstrations, or when you only care about the final results rather than detailed training logs. At the end of training, we read the last recorded loss value from the loss history to obtain the final loss, and the last recorded accuracy value from the accuracy history to obtain the final accuracy. These two values summarize how well the model performed after training with mixed precision. We then convert them to standard numeric form and print them to clearly report the model's final loss and accuracy. This script shows how to set a global mixed precision policy in TensorFlow to improve performance on supported hardware. It fixes random seeds for reproducibility, checks for a GPU, and configures the model to use a mix of 16-bit and 32-bit floating point numbers. A small subset of the MNIST dataset is loaded and reshaped for a simple convolutional neural network, whose layers automatically adopt this mixed precision policy. The model is compiled with a loss scale optimizer to keep training numerically stable, then briefly trained. Finally, the script reports the loss and accuracy to illustrate how mixed precision affects model performance. Loss scaling essentials. Loss scaling is a technique used to stabilize mixed precision training with formats like float16 or bfloat16. It multiplies the loss by a large factor before computing gradients, so the gradients fall into a safer numerical range and are less likely to vanish. Afterward, the gradients are divided by the same factor, so the actual parameter updates match what you would get without scaling. This approach lets you gain the speed and memory benefits of mixed precision while preserving the learning behavior of full precision training. There are two main styles of loss scaling: static and dynamic. Static loss scaling uses one fixed, usually large scaling factor throughout training, but it must be chosen carefully to avoid numerical underflow or overflow. Dynamic loss scaling, which is common in modern frameworks, automatically adjusts the scaling factor by monitoring gradients, skipping updates and reducing the scale when overflows occur. It then slowly increases the scale again when training appears stable. This adaptive behavior is especially helpful for complex models with changing gradient distributions, making mixed precision training more robust without manual tuning. Understanding loss scaling is important for interpreting mixed precision training and debugging your models on GPUs and TPUs. If you see infinities or not a number values, the scaling factor may be too high or some layers may not tolerate reduced precision, while very slow convergence can mean the scaling is too low and allows underflow. This is especially relevant when training language models with long sequences, where gradients can vary widely. Remember that loss scaling changes the numerical behavior, not the underlying optimization problem, which helps you decide when to rely on automatic settings and when to manually adjust the configuration for better performance. Future hardware needs. When planning deep learning infrastructure, it is important to recognize that mixed precision is now central to modern accelerators. New NVIDIA GPUs, Google TPUs, and similar AI chips are built to run efficiently with low-precision formats, such as float16, and B float 16. Therefore, you should evaluate hardware not only by its floating point operations per second, but also by how well it supports mixed precision workflows. Choosing newer devices with tensor cores can greatly shorten training times for large models compared to older, single precision GPUs. This alignment ensures your software's mixed precision settings fully benefit from the capabilities of your hardware. When planning hardware for deep learning, you need to consider how mixed precision affects both memory and bandwidth. Using lower precision formats lets you store more parameters, which can change what kind of GPU or TPU setup makes sense. For instance, some workloads may favor devices with less memory but higher bandwidth, while others need more memory per device. Understanding these trade-offs helps you choose hardware that will serve your current models and remain useful as they grow more complex. Mixed precision affects more than just compute speed. It also shapes choices about interconnects, storage, and energy use. As models grow and training spans many accelerators, communication between devices can become the main bottleneck. So high-speed links like NVLink are important to preserve performance gains. At the same time, organizations care about power costs and environmental impact, and mixed precision can reduce energy consumption in data centers and similar settings. By planning hardware with these trends in mind, you can build infrastructure that supports both current and future machine learning workloads. TensorFlow Profiling Essentials. TensorBoard Profiler Setup. To use TensorFlow profiling effectively, you integrate the TensorBoard Profiler into your training workflow. It records performance data from your program and shows it in an interactive web interface. You run your training with profiling turned on and point TensorBoard to the log directory where this data is saved. Then you can examine detailed performance metrics in your browser, from overall step times to timelines of individual operations. This setup is essential for analyzing and improving performance on anything from a single GPU to a large cluster. Begin by choosing a log directory to store profiling data, and make sure TensorBoard is set up and accessible, either remotely through a browser or directly on your local machine. After linking TensorBoard to this directory, start profiling during a training run to record performance data. Focus the profiling on a specific stable range of training steps to avoid collecting unnecessary information. In practice, this means waiting until the model and data pipeline are running normally, then profiling for a limited number of steps once initial setup overhead has passed. In complex setups like multi-GPU servers or TPU clusters, it is important to configure the TensorBoard Profiler correctly so performance data is captured and accessible. You must coordinate log directories across workers, enable profiling on the correct host, and make sure TensorBoard can read those logs. Often, each device writes profiling data to a shared storage system, and a single TensorBoard instance is used to visualize all results. On TPUs, the profiler integrates with the TPU runtime to record specific performance metrics. Overall, you need a clear path from the training job to the log directory, then to TensorBoard, and finally to your browser for effective performance analysis. Python code, TensorBoard Profiler Setup. This material introduces a simple example that demonstrates how to set up and use the TensorBoard Profiler. It uses a very small Keras model to keep the focus on the profiling process rather than model complexity. The script is intended to be run in Google Colab, making it easy to experiment with profiling tools in a cloud environment. This line is simply a comment explaining that TensorFlow should be installed only if needed. It shows a pip command for installing TensorFlow version 2.20, but the command is not actually run in the script. The comment is included to guide users who may need to install TensorFlow manually, and to help ensure they use a compatible version with the rest of the code. We start by importing 3 useful Python libraries. The operating system library lets us interact with the system for tasks like managing files and folders. The pathlib library provides a more convenient, object-based way to work with file system paths. Finally, the random library allows us to generate random numbers, which is helpful for things like setting seeds to make experiments reproducible. We begin by importing TensorFlow, a library that lets us efficiently build and train machine learning and deep learning models. From TensorFlow, we then import Keras, a high-level interface that makes it easier to define neural networks. Keras provides convenient tools for creating layers, assembling models, and managing the training process. Together, these imports prepare the environment for constructing and training our neural network later in the script. We set a fixed seed value, in this case the number 42, so that any random operations in our code produce the same results every time it runs. This practice is important for reproducibility, especially when running experiments or debugging. By applying this seed to Python's random module, we ensure that all random numbers it generates are consistent across different runs. This makes it easier to compare results and track down issues in our programs. We set TensorFlow's random seed to the value 42, so that any operation involving randomness will give the same result every time the code runs. This makes the behavior of the model predictable and repeatable. Such reproducibility is important for running experiments consistently and for debugging issues reliably. This command displays the version of TensorFlow that is currently in use. It provides a quick way to check which version is installed in your environment. Knowing the exact version is important because it can affect compatibility with other code and libraries. Verifying the version helps you avoid errors that come from using mismatched software components. The code uses TensorFlow tools to check whether any GPU devices are available. It asks for a list of all physical devices of type GPU to see if the program can use GPU acceleration. This is important because deep learning tasks usually run much faster on a GPU. If no GPUs are detected, the program automatically falls back to running on the CPU instead. This code checks whether TensorFlow can detect any physical graphics processing units, or GPUs, on the system. If at least one GPU is found, it sets the device type to GPU. If not, it falls back to using the central processing unit, or CPU. This device description is then used later to indicate which kind of hardware the script will most likely use for its computations. This code checks whether any physical GPUs are available, and then prints a message indicating whether TensorFlow operations will likely run on a GPU or on the CPU. If at least one GPU is detected, it reports that the device type is GPU. Otherwise, it reports CPU. Knowing this helps you understand the hardware context in which your model will execute, which is especially important in environments like Google Colab, where GPU availability can greatly affect performance. We define a base directory to store profiling logs, using a path handling library that treats file paths as objects. This directory, named for profiler logs, will hold the data we collect while monitoring model performance during training. Keeping all profiling data in one place makes it easier to analyze and debug how the model runs. Using this path library also ensures the directory path works correctly across different operating systems. This code makes sure the log directory exists on the disk before writing any data. It uses a directory creation function from the pathlib library that can also create any missing parent folders. It is set up so that no error occurs if the directory is already there. This preparation is important for reliably storing profiling logs when you run TensorBoard. We create a dedicated folder for this run's logs by combining the main log directory with a subfolder named run_01. This gives each run its own separate place for log files. Organizing logs this way makes it easier to keep runs distinct. It also simplifies later analysis and comparison of results across different runs. The code makes sure a directory for the current training run exists, so it can store profiling summaries and other logs. It automatically creates any missing parent folders and avoids errors if the directory is already there. This setup keeps training logs organized and easy to access later, which is especially important when using tools like TensorBoard to visualize training metrics. This code prints the path to the log directory that TensorBoard will use, so you know exactly where the profiling data is being saved. Knowing this location lets you return later to inspect and analyze the stored results. Converting the directory path to a string ensures it appears in a clear, readable form when it is displayed. The code uses Keras to load the MNIST dataset, a standard collection of handwritten digit images for training image processing models. The loading function returns both training and test data, but in this case, only the training portion is needed. The images are stored in one variable and their corresponding digit labels in another. The unused test data is assigned to an underscore to indicate that it is intentionally ignored for this demonstration. The code first converts the MNIST training images to 32-bit floating point numbers, a standard format for numerical work in TensorFlow, so they can be processed correctly by the neural network. It then rescales the pixel values from their original range of 0 to 255 down to a range of 0 to 1. This normalization step puts all inputs on a consistent scale, which helps the model train more efficiently and improves convergence and stability during learning. This line of code adds an extra dimension to the training images, so they are compatible with convolutional layers in TensorFlow. It changes each image from a two-dimensional array to a three-dimensional one, where the new third dimension represents the single color channel. Convolutional layers require this channel dimension in their input, even for grayscale images such as those in the MNIST dataset. Without this added access, the data would not match the expected input shape for these layers. We limit the subset size to 2,000 examples, so the script runs quickly. Using only a small portion of the dataset keeps the training process short and easier to manage. This approach is especially useful for quick tests, experiments, or demonstrations, where full-scale training would take too long. We make sure the chosen subset of training data never exceeds the total number of available samples. To do this, we take the smaller value between the desired subset size and the actual size of the training set. This prevents the code from trying to access data that does not exist. As a result, we avoid errors and unexpected behavior during the training process. We create a smaller training subset by taking only a limited number of images from the full training set. This reduced dataset is easier and faster to work with during experimentation. We then select the corresponding labels for these images, so that each image still matches its correct label. Keeping the features and labels aligned in this way is essential for training the model accurately. The code prints the shape of the training subset to quickly confirm that the data has been prepared correctly. By checking these dimensions, it verifies that the number of samples and features match what the model expects. This simple step helps ensure the training process will run on properly structured data. We build a Keras sequential model by stacking layers in order. The input layer matches the MNIST image size of 28 by 28 pixels with a single channel. We then apply a two-dimensional convolutional layer with 16 small filters and a ReLU activation to learn local features, followed by a max pooling layer that reduces the spatial size of the feature maps. The result is flattened into a one-dimensional array and passed to a dense layer with 32 units and ReLU activation for further processing. Finally, a dense output layer with 10 units and a softmax activation produces class probabilities for the 10 MNIST digit categories. The model is now being prepared for training by choosing its main settings. It uses the Atom optimizer with a learning rate of 0.001, a common and efficient choice for training neural networks. The loss function is set to sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are integers. During training, the model will also track accuracy as a metric, so we can monitor how well it is learning on the training data. We set up a TensorBoard callback to record scalar values during training and store them in a specified log directory. To keep the logs simple and compact, we disable histogram recording and do not save images. At the same time, we enable logging of the computational graph so we can visualize the model's architecture while focusing on the most essential training data. We define a function that runs a short training session, and inside it, we create a TensorBoard Profiler callback. This profiler is configured to monitor only a specific range of batches, from batch 20 to batch 30. By focusing on these batches, we collect detailed performance data during that part of training. This information helps us analyze how the model behaves and identify opportunities to optimize its performance. The model is trained using the Keras fit method with MNIST images and their digit labels as input. Training runs for 2 epochs, so the model goes through the entire dataset twice, and it updates its weights after every 64 images. The training output is silenced, but TensorBoard is used to log metrics, and an additional callback profiles selected batches to analyze performance. Together, these settings help monitor and optimize how the model learns during training. This function returns the model's final training accuracy by taking the last value from the accuracy list stored in the training history. The history object is created during training and records metrics such as accuracy for each epoch. By using the last recorded accuracy, the function quickly reports how well the model performed at the end of training. The program calls a training function that both trains the model and collects profiling data about its performance. When this process finishes, the function returns a single value representing the final training accuracy. This accuracy value shows how well the model performed on the training data at the end of training, and it is stored for later use or analysis. This code displays a message that tells you how to open the profiler in a Google Colab environment. It is meant to help you analyze your model's performance using TensorBoard. By following the instructions shown in the message and running it in a Colab cell, you can launch the profiler interface and start examining how your model behaves during execution. In a Jupyter notebook, you can load the TensorBoard extension using a special magic command that activates TensorBoard inside the notebook. Once enabled, this lets you view and explore training logs and profiler data directly in the notebook interface. This integration makes it easier to monitor how your model is learning and to debug performance issues without leaving the notebook environment. The code prints a command you can run in a Jupyter or Colab cell to start TensorBoard and view profiling data. Running this command launches TensorBoard with the chosen log directory, so you can inspect training logs and profiler outputs. The log directory is converted to a string to ensure it works correctly in the command format. At the end of the script, the final training accuracy of the model is printed. This value is rounded to 4 decimal places to keep it clear and precise. Showing this result confirms that training has finished and gives a quick summary of how well the model performed during training. This script demonstrates how to set up TensorBoard profiling for a simple Keras model in Google Colab. It first makes the run reproducible, checks for a GPU and falls back to the CPU if needed, and creates a log directory for TensorBoard data. It then loads and preprocesses a subset of the MNIST dataset and defines a small convolutional neural network compiled with the Atom optimizer. The model is trained briefly, while a TensorBoard callback records profiling information for selected batches. After training, the script reports the final accuracy and explains how to start TensorBoard in Colab so you can inspect the model's performance and resource usage. Reading trace timelines. When you open a profiling trace in TensorBoard, you are looking at a timeline of what your model and hardware are doing during training or inference. Time runs along the horizontal axis, and the vertical axis shows tracks for components such as the CPU, GPUs or TPUs, and TensorFlow activities. Each colored block on these tracks represents an operation, like a matrix multiplication or a data transfer. By zooming into a single training step, you can see the order and duration of these operations, which helps you judge how efficiently your model is using the available resources. When reading a performance trace, first identify the boundaries of each training step, then focus on what happens during a typical step. You will usually see data prepared on the CPU, transferred to the accelerator, then heavy computation on the GPU or TPU, followed by gradient updates. If the accelerator is idle while the CPU is busy, the model is waiting for data, and the bottleneck is in data processing. If the accelerator is fully active and the CPU is mostly idle, the bottleneck is in the computation itself. For example, image processing on the CPU can leave the GPU waiting in vision tasks, while language models often keep the GPU fully occupied with complex operations. Once you understand trace timelines, you can use them to spot subtle performance problems. Gaps between operations on the accelerator track may reveal synchronization points or unnecessary data transfers. Many short GPU tasks can indicate too much control flow or operations that should be batched. Limited overlap between input handling and computation may point to weak prefetching or parallelism. By reading these patterns, you can link performance metrics to specific behaviors in your model and data pipeline. Python code, reading trace timelines. This script introduces the basics of profiling in TensorFlow. You will learn how to capture a performance trace and then view it to understand what is happening during execution. The main goal is to recognize simple patterns in the timeline, so you can start interpreting profiling results. By focusing on these basic patterns, you build a foundation for more advanced performance analysis later. The commented line refers to installing TensorFlow, but because it is commented out, it is treated as optional or already completed. Its purpose is to ensure that TensorFlow version 2.20 is available, since the rest of the script depends on it. The comment also acts as a reminder to verify the TensorFlow installation if problems occur when running the code. We start by importing three key tools. The operating system module lets us work with the file system, such as creating folders. The random module provides random number generation, which is useful for tasks like shuffling data. Finally, we import NumPy, a numerical computing library that supports large multi-dimensional arrays and matrices, and offers many mathematical functions to work with them. We start by importing TensorFlow, which we use to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers tools from Keras, which give us components like convolutional and dense layers. Together, these imports provide the basic building blocks needed to define and train our model architecture. We start by setting a seed value of 42 to make all random operations reproducible. First, we set the seed for Python's built-in random number generator, so it produces the same sequence each time. Then we set the seed for the NumPy random number generator for consistent NumPy results. Finally, we set the seed for TensorFlow's random number generator, so operations like initializing neural network weights behave the same across runs. This line displays the version of TensorFlow that is currently in use. Knowing the exact version helps you check compatibility with other tools and libraries. It is also useful for debugging, because different TensorFlow versions can have different features or behaviors. By printing the version, you can quickly confirm that your environment matches what your code expects. The code first checks whether a physical graphics processing unit is available through TensorFlow's configuration. If a GPU is found, it selects the first GPU so that computations run there. If no GPU is available, it instead selects the first CPU, so the work runs on the processor. This approach automatically uses the best available hardware to improve performance. This code prints a message that tells you which device is being used to run the model. It checks the available hardware and decides whether to run on a graphics processor or on the main processor. The printed message makes it clear which type of computational resource is being used for the task. The code uses Keras to load the MNIST dataset, a standard collection of images of handwritten digits used for training image processing models. The data is divided into training and testing parts, but here only the training portion is taken. The images are stored in one variable and their digit labels in another. This prepares the training data so it can be fed into a model for learning. To speed up profiling, the code uses a smaller training dataset by taking only the first 2,000 samples from the original data, including both images and their labels. This reduced subset makes model training and profiling run faster. As a result, it becomes easier to analyze performance without the extra time and computation required to process the full dataset. The code prepares the training images by converting them to a floating point format and scaling their pixel values to range between 0 and 1. It does this by changing the data type to a floating point type and dividing each pixel value by 255. This normalization keeps the pixel values consistent and helps improve the model's performance and stability during training. We use a function from the numerical library to expand the dimensions of the training images by adding an extra channel dimension. This new dimension is placed at the end of the image shape, so each image changes from a two-dimensional array to a three-dimensional array with one channel. This format is required so that the convolutional layers in the neural network can process the images correctly. Without this added channel dimension, the convolutional neural network would not receive the input in the structure it expects. Before building the dataset, the code prints the shape of the training data to confirm that it has been processed correctly and matches the format the model expects. This check is especially important after steps like normalization and adding a channel dimension, which can change the data's structure. Verifying the dimensions in this way is a key debugging step that helps ensure the data pipeline is correct before starting model training. We begin by building a TensorFlow data pipeline using the Dataset Application Programming Interface. This creates a dataset object from the training images and labels, where each image is paired with its corresponding label as a single data point. Using the method that forms the dataset from slices of these arrays lets TensorFlow manage and process the data efficiently during training. This setup is important for working with large datasets and taking advantage of TensorFlow's performance optimizations. The dataset is first shuffled using a buffer of 2,000 examples and a fixed seed, so the random mixing is reproducible for each training run. This randomization before every epoch helps the model learn more effectively by preventing it from seeing data in the same order each time. After shuffling, the data is grouped into batches of 64 samples, allowing the model to process many examples at once. This batching greatly improves computational efficiency and speeds up the overall training process. This code uses TensorFlow's prefetching feature to make the data pipeline more efficient. By enabling automatic tuning, it lets data loading run in parallel with model computation. As the model processes one batch, the next batch is prepared in the background. This overlap reduces idle time and increases overall training throughput. We define a function that builds and returns a simple convolutional neural network using a sequential Keras model. It starts with a two-dimensional convolutional layer with 16 3x3 filters and ReLU activation, taking 28 by 28 grayscale images as input, followed by a 2x2 max pooling layer to reduce spatial size. The output is then flattened and passed to a dense layer with 32 units and ReLU activation. A final dense layer with 10 units and softmax activation produces a probability distribution over 10 classes. The model is compiled with the Atom optimizer, uses sparse categorical cross-entropy loss for integer labels, and tracks accuracy as its main performance metric. We first set up a directory called logs profile demo where TensorBoard will store its profiling trace logs. This directory helps keep the profiling data organized and easy to find later. We then use the operating system tools to create the directory if it does not already exist, so the folder structure is ready for saving logs. This preparation ensures that all profiling information is properly recorded and accessible. The code prints a message to the console that tells you where the trace logs are being saved. This directory path is important because it shows you where to find the logs later. Knowing this location is especially useful when you want to open the logs in TensorBoard to visualize profiling data. We use a TensorBoard Profiler callback to monitor model performance during training, saving logs in a chosen directory. To keep the logs lightweight, we turn off histogram logging of weights and do not record the computational graph or images. We also configure profiling to run only on the second and fourth training batches. This focused setup lets us analyze specific parts of the training process without generating excessive data. Within the chosen device, either a GPU or CPU, we create a new instance of the simple convolutional neural network defined earlier and train it using the prepared training data pipeline. The training is limited to one epoch with only 10 steps to keep the profiling process fast. Verbosity is turned off so no training output is displayed. A profiler callback is included to record performance data for selected batches, which can later be examined in TensorBoard to analyze how the training behaves. This code simply tells you how to open TensorBoard to view your model's performance data. It prints a message in the console that instructs you to run a specific command in your terminal. That command points TensorBoard to the directory where the profiling logs are stored. Once you run it, you can use TensorBoard to visualize the performance traces of your TensorFlow model. This script shows how to use TensorFlow's profiler to capture and inspect the training behavior of a simple convolutional neural network on a small subset of the MNIST dataset. It sets deterministic seeds, checks for a GPU, loads and normalizes 2,000 images, and builds an efficient data pipeline with shuffling, batching, and prefetching. A compact convolutional model with 2 convolutional layers and dense layers is compiled with the Atom optimizer and sparse categorical cross-entropy loss. A TensorBoard Profiler callback is configured to record traces for selected training batches during a short single epoch run. After training, you can open TensorBoard to view the profiling logs and analyze the timing and performance patterns of the training process. Finding performance bottlenecks. When using TensorBoard's Profiler, your main goal is to understand where time and resources are spent during training, so you can spot performance issues. Compare the total time for each training step with the time used by model computation, the input pipeline, and other overhead. If a large portion of each step occurs before major computation starts, it likely indicates an input bottleneck, where the GPU or TPU is waiting for data. If the device is busy but throughput is still low, the cause may be inefficient model operations, such as many small kernels or too much synchronization. By examining these high-level summaries, you can decide whether to optimize the input pipeline, adjust the model architecture, or refine the training loop configuration. After forming a high-level hypothesis about performance issues, use the trace view to pinpoint which operations or stages are causing slowdowns. The timeline shows events on both the host and the accelerator for each training step, and their length and order reveal important patterns. Long idle periods on the accelerator usually mean it is waiting for work, often because data loading or CPU preprocessing is too slow, such as image augmentations in computer vision models. In contrast, many short kernels with frequent switches suggest fragmented operations that reduce hardware efficiency, as can happen in natural language models with separate embedding lookups. A profiler helps you see whether performance bottlenecks come from the workload itself or from how you implemented it. Memory problems, such as frequent data transfers or large tensor allocations, can interrupt computation and slow things down. In systems like recommendation engines, repeated transfers often mean the input pipeline needs optimization. If layers like matrix multiplications take time but do not fully use the hardware, it may point to inefficient batch sizes or tensor shapes. By spotting these patterns and adjusting your configuration, you can reduce bottlenecks and improve overall performance. Python code, finding performance bottlenecks. This script introduces the basics of profiling in TensorFlow by comparing slow and fast input pipelines. It helps you visualize how different pipeline designs affect performance. You can use it to quickly identify simple bottlenecks in your data input process and guide improvements to make your models run more efficiently. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. Using this specific version makes sure the script runs with the expected features and behavior. Because different TensorFlow versions can work differently, fixing the version helps avoid unexpected changes. This keeps the script consistent and reliable across different environments. We start by importing 3 useful libraries. The operating system library lets us interact with the system, for example, to work with files or environment settings. The time library provides tools for handling time, such as measuring how long code takes to run or adding delays. The random library allows us to generate random numbers, which is helpful for tasks like random sampling or controlling randomness with a fixed seed. We start by importing TensorFlow, a library used for machine learning and deep learning, so that its tools are available in our program. After that, we check which version of TensorFlow is installed. Knowing the version is important because different versions can have different features or behaviors. This helps us make sure our code is compatible with the TensorFlow setup we are using. We set the seed value to 42 so that any random operations in our code give the same results every time we run it. Using this seed to initialize the random module makes the sequence of random numbers repeatable. This reproducibility is important because it allows us to get consistent, predictable outcomes across different runs of the program. We set the random seed for TensorFlow using a predefined value so that any random operations it performs will always give the same results each time the code runs. This makes the behavior of the model predictable and consistent. It is especially important for reproducing experiments and for debugging, because it allows you to reliably compare runs and track down issues. This line displays the version of TensorFlow currently in use. It provides a quick check that the correct version of the library is installed and running. Confirming the version helps ensure compatibility and that all features and functions work as expected. The code uses a TensorFlow function to list all physical devices of type GPU, which lets you check whether the system has any graphics processors available. Knowing this is important because GPUs can handle many operations in parallel. As a result, if a GPU is present, computations can run much faster than if they were done only on a CPU. The code checks TensorFlow's list of physical devices to see if any GPUs are available. If it finds one or more GPUs, it chooses to run operations on a GPU. If no GPUs are present, it falls back to using the CPU instead. This selection ensures TensorFlow uses the best available hardware for performance. This line displays whether the program will mainly use a graphics processor or a central processor for its computations. It relies on a device choice made earlier in the script, which checks if a graphics processor is available and otherwise falls back to the central processor. Sharing this information helps users understand what hardware their code is running on, which is important for judging and optimizing performance. We begin by creating a small synthetic dataset for profiling. We choose 2048 samples, which sets how many data points the dataset contains. We also set the feature dimension to 32, meaning each data point has 32 features. These choices give us a simple but realistic dataset for testing and performance profiling. This code uses TensorFlow to create random feature data drawn from a normal distribution, forming a tensor with a chosen number of samples and feature dimensions. By generating these controlled random values, it simulates real-world data in a simple, repeatable way. This synthetic dataset is then used to test and profile how well the model performs. This code generates binary labels for each data point by summing all the values in its feature vector and checking whether that sum is greater than 0. It uses TensorFlow's reduce sum operation to compute the total for each vector, then compares the result to 0 to decide the label. If the sum is positive, the label is set to 1, otherwise it is set to 0. Finally, the labels are converted to an integer type with TensorFlow's cast operation, so they are ready for further processing. Before building the datasets, the code checks that the number of feature samples matches the number of labels. This guarantees that every feature vector has a corresponding label, which is essential for correct model training. If these counts do not match, it signals a data mismatch that could cause errors during training. This simple check helps ensure the data is consistent and reliable before the model is trained. We build a simple Keras model using the sequential API, which stacks layers one after another. The model begins with an input layer that matches the feature dimension of the data. It then uses a dense layer with 64 units and a ReLU activation to introduce nonlinearity. Finally, it adds a dense output layer with a single unit and a sigmoid activation, producing values between 0 and 1 for binary classification tasks. The model is now being prepared for training by choosing key settings. It uses the Atom optimizer with a learning rate of 0.001, which is a common and effective choice for deep learning. The loss function is set to binary cross-entropy, which fits binary classification problems. Accuracy is added as a metric to track how well the model performs during training. With this configuration, the model is ready to learn effectively from the data. We begin by building a deliberately slow input pipeline using TensorFlow's data tools. The feature and label tensors are converted into a dataset by slicing them into individual elements and pairing each feature with its matching label. This simple, unoptimized setup acts as a baseline so we can later compare its performance to a more efficient input pipeline. We apply a mapping function to the dataset to intentionally introduce a small delay in processing. Using TensorFlow's mapping capability, we define a lambda that takes features and labels, then calls a Python function through TensorFlow's PyFunction mechanism. This Python function pauses for 1 millisecond to mimic a computationally expensive step, then returns the original features while leaving the labels unchanged. The result is a deliberately slowed data pipeline that we can later compare against a more optimized version to study performance differences. The setShapes function is used to preserve the shape information of the data as it moves through the slow pipeline. Inside this function, a method is called on the input to explicitly set its shape so it matches the expected feature dimension. This step is important because it keeps the data structure consistent throughout processing. The function then returns both the input and its label, allowing the dataset to continue with the correct shape information in place. The code uses a mapping function on the slow dataset to explicitly set the shapes of its elements. This setShape step makes sure that all input features have consistent and known shapes. Having fixed shapes is important for keeping the data pipeline reliable and for supporting TensorFlow operations that depend on knowing data shapes in advance. It is especially crucial in the slow pipeline, where earlier transformations might otherwise hide or change shape information. The code processes the slow dataset by grouping it into batches of 32 samples, so the model can train on multiple examples at once. This batching step makes training more efficient. It then uses prefetching with a small buffer to prepare the next batch while the current one is being processed. By overlapping data preparation with model execution, prefetching reduces idle time and improves overall throughput. We begin by building a fast, efficient input pipeline using TensorFlow's dataset tools. This means taking the feature and label tensors and turning them into a dataset object. Doing so lets TensorFlow handle data loading, manipulation, and optimization for us. As a result, we can work more effectively with large datasets and keep the training process running smoothly. To prepare the data pipeline, we first shuffle the dataset with a buffer of 512 examples to randomize the order and improve training. We then group the data into batches of 32 samples, so the model can process several examples at once more efficiently. After that, we cache the dataset in memory so later training epochs run faster. Finally, we prefetch data with TensorFlow's automatic tuning, which overlaps data loading with model execution to reduce idle time and increase throughput. We use a helper function to measure how long one training epoch takes. Before starting the timing, the function runs a single training step on one batch of data to warm up the model. This warm-up removes any initial setup overhead from the measured epoch time. The step uses the model's method that performs one gradient update on the batch, runs silently, and its output is ignored, since its only purpose is to prepare the model for accurate timing. The code records the current time at the start of an epoch to measure how long that training epoch takes. This timing information is used to precisely track the duration of training. By comparing these measured times, you can evaluate and compare the performance of different input pipelines. This code runs the model for a single training epoch using the fit method, so the model sees each sample in the dataset exactly once. Training output is turned off by setting the verbosity to 0. The number of steps in the epoch is set by dividing the total number of samples by the batch size, ensuring the entire dataset is processed in one pass. This setup is used to measure how long one complete pass through the data takes, which allows comparison of different input pipeline performances. The code measures how long an operation takes by recording a start time, then subtracting it from the current time. This difference gives the elapsed time in seconds. That value shows the duration of a process or function and is useful for checking and comparing performance. This code takes the final loss value from the training history. It looks up the loss entry in the history dictionary, which stores a list of loss values recorded during training. It then selects the last value in that list, ensuring it uses the most recent loss. Finally, it converts this value to a floating point number for consistent use in later calculations or reporting. The code takes the final accuracy value from the training history by looking up the accuracy entries stored for each epoch and selecting the last one in the list. This last value represents the accuracy from the most recent training epoch. It is then converted to a floating point number to keep the format consistent. This makes the result easier to report accurately and to use in any further numerical calculations. The code prints a short summary line that describes the dataset used and reports how long the epoch took in seconds, rounded to 3 decimal places. It also shows the final loss and accuracy, each rounded to 3 decimal places. This compact output makes it easy to compare performance across different input pipelines and see how pipeline design affects training efficiency. We begin by running a timing function for one training epoch using the slow input pipeline. This function takes the slow dataset and a description, in this case, the phrase slow pipeline epoch, which will appear in the output summary. Its goal is to measure how long it takes to train the model for a single epoch when the input pipeline includes an intentional delay. By doing this, we can see how an inefficient input pipeline affects the overall training time. We now run a timing function for one training epoch using the fast input pipeline, labeled as the fast pipeline epoch. The goal is to measure how quickly the model can complete a single epoch when the data pipeline is optimized. This fast pipeline improves efficiency by shuffling, batching, caching, and prefetching data. Comparing its timing to a slower pipeline shows how input pipeline design affects overall training performance. The final print statement shows how the design of your input pipeline affects total training time. By comparing the execution times of slow and fast pipelines, you can see how different data handling strategies change performance. This understanding is essential when using profiling tools to find bottlenecks in your code. With these insights, you can optimize data processing and make your training more efficient. This script shows how to find performance bottlenecks in TensorFlow input pipelines by comparing a slow and a fast version. It builds a synthetic dataset with random features and binary labels, then trains a simple neural network using the atom optimizer and binary cross-entropy loss. The slow pipeline adds an artificial delay to each data point, while the fast pipeline uses techniques like shuffling, batching, caching, and prefetching. Both pipelines reach similar accuracy and loss, but the slow one takes much longer per epoch, illustrating how efficient input pipeline design can greatly reduce training time in machine learning workflows. Numerical stability essentials, NaN and Int detection. When training deep learning models, NaN and Int values can seriously disrupt learning because they arise from undefined operations or numbers that exceed floating point limits. Once they appear, they can quickly spread through the model, corrupting the loss gradients, and weights so that loss values may become NaN, and evaluation metrics may no longer make sense. Detecting these invalid values early is essential because they usually signal deeper numerical instability in the model's design or settings. Ignoring them can waste computation and lead to misleading conclusions about model performance. To detect NaNs and Infs during training, combine automated monitoring with manual checks. Track the loss curve and key metrics, and treat sudden jumps to NaN or extremely large values as signs of numerical problems. Configure your training framework to warn you or stop the run when these values appear, which is especially important for long or remote experiments. You can also add checks inside custom layers or unusual activation functions to confirm their outputs stay finite, ensuring the model learns from valid computations rather than numerical errors. Once you detect NaNs or Infs in your model, the next step is to find out exactly where and when they appear. You can do this by rerunning training with more detailed logging or smaller batches to narrow down which layer or operation is producing them. Often, these invalid values show up only for certain kinds of inputs, such as very high pixel values or extreme sensor readings, which can reveal issues like unscaled inputs or unstable computations. By understanding these conditions, you can apply targeted fixes such as input normalization or gradient clipping, moving from simply noticing the problem to actually resolving it. Python code, NaN and Inf detection. This script introduces the basics of detecting not a number and infinity values when working with TensorFlow tensors and a small model. It demonstrates how to identify these problematic values during training so you can handle them safely. The main goal is to show simple, reliable checks that help keep the training process stable and correct. In some setups, TensorFlow is not installed automatically, so an optional command is provided to install version 2.20. This command is commented out, meaning it does not run by default. You can enable and run it when needed to make sure TensorFlow is available and the environment is properly configured. We begin by importing TensorFlow because it provides the core tools needed to build and manage the tensors and models used in this script. Tensors are the main data structures in the code, and TensorFlow supplies the functions to create, manipulate, and analyze them. This import is essential for carrying out machine learning tasks in the script, including checking tensors for special values like not a number and infinity. We set the random seed in TensorFlow to a fixed value so that any random operations give the same results every time the code runs. This makes the behavior of the model predictable and repeatable. It is especially important when debugging or when comparing model performance across different runs, because it ensures that differences in results are not caused by random variation. This line displays the version of TensorFlow that is currently in use. It provides a quick way to check which version of the library is installed. Knowing the exact version is important because it affects compatibility with other tools and can help when diagnosing and fixing issues. We begin by creating a small tensor using TensorFlow's constant function that holds the three floating point values 1, 2, and 3. Its data type is explicitly set to 32-bit floating point to keep numerical operations consistent and precise. This tensor is considered safe because all its values are finite, with no infinities or not a number entries. Establishing this clean, well-defined tensor is important so we can later compare it with tensors that may contain problematic values. We create a tensor called InfTensor using TensorFlow's constant function that holds two values, the number 1 and the largest number that can be stored in a float 32 data type. This setup is used to show what happens when computations involve extremely large values. By working with this tensor, we can see how certain operations can overflow and produce infinity during numerical calculations. we take a tensor whose value is already at the maximum floating point number and multiply it by 2 to intentionally exceed the representable range. This causes the result to become infinity. The example shows how TensorFlow safely produces an infinity value when operations go beyond what floating point numbers can normally represent. We create a tensor filled with zeros using the float32 data type, specifically to use it in operations that will produce NaN or not a number values. By starting with zeros, we can perform a division where 0 is divided by 0, which is undefined and results in NaN. This setup is used to test how the code behaves and how it handles these undefined numerical results. In this step, we divide a tensor of zeros by itself to deliberately create values that are not a number. Since 0 divided by 0 is undefined in mathematics, this operation reliably produces these invalid values. Doing this on purpose is important for testing how the system detects and handles not a number entries inside tensors. We use a helper function called summarizeBadValues that takes a tensor and its name and prepares it for checking numerical issues. Inside this function, the tensor is first converted to a TensorFlow float32 type. This conversion is important because detecting values like not a number and infinity only works correctly on floating point tensors. By ensuring the tensor is in this format, we can reliably check for any non-finite values it may contain. This code uses TensorFlow to create a Boolean mask that marks which elements in a tensor are not a number values. It checks each element and sets the mask to true where the element is a NaN and false otherwise. This mask can then be used in later steps to count how many NaN values there are or to handle them appropriately during further processing. This code uses TensorFlow's math tools to build a mask that marks any infinite values in a tensor, including both positive and negative infinity. The mask acts like a detector, highlighting where these problematic values occur. This step is important because it helps identify numerical issues early, so infinite values can be handled properly during further computations. This code counts how many entries in a tensor are not a number values. It first creates a mask that marks each not a number position as true, then converts that mask into integers where each true value becomes 1. Finally, it adds up these ones to get the total number of not a number values in the tensor. This code counts how many entries in a tensor are infinite. It starts with a Boolean mask that marks infinite values as true and all others as false. The true values are converted to ones and the false values to zeros. Finally, it sums these ones and zeros to obtain the total number of infinite values in the tensor. This code prints a short summary of a tensor, reporting how many values are not a number and how many are infinite. It labels the output with a given name for the tensor, then shows the count of not a number values, followed by the count of infinite values. This gives you a quick way to spot problematic entries in the tensor without inspecting all of its elements. We use a function to summarize bad values in a tensor, passing in the safe tensor and labeling it as the safe tensor. This function scans the tensor for any values that are not a number or that are infinite, and then reports what it finds. In this case, all entries are finite, so the summary confirms there are no invalid values. This tells us the tensor is clean and safe to use in further computations. We use a special function to summarize invalid values in a tensor, focusing on results that are infinite. This function scans the tensor, checks for any values that are not a number or are infinite, and then prints a brief report. In this case, it confirms that the tensor does contain infinity values, which were produced earlier by multiplying a tensor holding the maximum floating point value by 2. We use a function designed to summarize bad values and pass it the tensor that may contain not a number entries. This function scans the tensor for any not a number or infinite values and reports how many of each it finds. Our main goal here is to verify that the tensor does in fact contain not a number values, which matches what we expect from the earlier operations. We are building a very simple neural network using TensorFlow's Keras interface. The model is sequential, meaning each layer feeds directly into the next. It takes a single input feature and passes it to one dense layer with a single neuron and no bias term. This minimal design is used to show how even a tiny model can run into numerical problems like overflow during training. We deliberately assign an extremely large weight to the model's first layer to force numerical overflow. This is done by setting the weights to a constant value of 10 to the power of 20 using a 32-bit floating point type. With this setup, the model becomes numerically unstable during training, clearly illustrating how extreme parameter values can break the computation. We create a small batch of input values using TensorFlow's constant function, containing the numbers 2 and 3, arranged as a two-dimensional tensor. We set the data type to 32-bit floating point, so it matches the model's expected input format. This prepares the batch so it can be passed directly into the model during the forward pass in training. We use TensorFlow's built-in mean-squared error loss function to measure how well the model's predictions match the actual target values. This loss is computed as the average of the squared differences between predicted and true values. Because it squares the errors, larger mistakes are penalized more heavily than smaller ones. This makes mean-squared error a common and effective choice for training regression models. We use a basic optimizer called stochastic gradient descent, or SGD, with a small learning rate of 0.01. A small learning rate means the model's weights are updated slowly and carefully during training. This helps keep the training process stable and reduces the risk of numerical problems such as overflow or underflow, especially with models or data that might be unstable. We begin by using TensorFlow's gradient tape context, which records the operations needed for automatic differentiation. Inside this block, we run a forward pass by feeding the input data through the model while it is in training mode. The model then produces predictions based on its current parameters. This recorded computation is what later allows us to calculate the gradients of the loss with respect to the model's weights during training. The code builds a target tensor that has the same shape as the predictions tensor, but fills it entirely with zeros. It uses the TensorFlow function that creates a zero tensor, matching another tensor's dimensions, which makes it easy to compare predictions and targets during loss calculation. By choosing 0 as the target value, the setup assumes the model should learn to produce outputs close to 0. This is often used for testing or when working with normalized outputs. The code uses the mean-squared error loss function to measure how far the model's predictions are from the true target values. This function compares predicted and actual values and produces a single numerical loss value. That value summarizes the model's performance and is then used to guide and update the model during training. Inside the gradient tape, we compute how the loss changes with respect to each trainable weight in the model. These values are the gradients used in backpropagation. They tell us how much each weight contributes to the loss. By capturing these gradients, we can later update the weights in a direction that reduces the loss during training. We now examine the predictions tensor to check for any invalid values such as NaN or Inf. To do this, we call a helper function that summarizes bad values, passing in the predictions tensor and the label predictions. This function scans the tensor, counts any NaN or Inf entries, and reports a summary of these problematic values. This validation step is important to confirm that the model's predictions are numerically sound and to help diagnose issues that may occur during training. We now inspect the gradients to see if they contain any not a number or infinite values. To do this, we call a helper function that summarizes problematic values, giving it the first gradient tensor and labeling it as gradients. This check reveals whether any non-finite values are present, which can signal numerical instability or other issues during training. Identifying these bad values early helps diagnose and correct problems in the training process. The code first checks whether all gradient values are finite, meaning none of them are not a number or infinite, because such values could destabilize training. If every gradient passes this check, the optimizer uses them to update the model's weights so it can learn from the current batch of data. If any gradient is not finite, the code prints a warning and skips the update. This prevents the model from being changed using invalid values and helps maintain a stable, reliable training process. This script shows how to detect not a number and infinity values in TensorFlow tensors and during model training to maintain numerical stability. It creates both safe tensors and tensors that deliberately contain invalid values, then uses a helper function to count how many problematic entries each one has. A simple model with a very large weight is used to trigger overflow, and during a training step, the script checks predictions and gradients for not a number and infinity values. If any are found, the parameter update is skipped so that only finite values are used. This approach emphasizes the importance of monitoring and handling numerical issues in machine learning workflows. Gradient clipping basics. Gradient clipping is a method used to control exploding gradients, which happen when gradient values become excessively large during backpropagation and make training unstable. This problem is common in deep or recurrent networks and when working with long or variable sequences. To prevent this, gradient clipping sets a maximum allowed size for the gradients before updating the model's parameters. By limiting how large the error signal can be in a single step, it helps keep training stable and prevents the model from diverging. Gradient clipping is used to prevent gradients from becoming too large during training. One approach, clipping by value, limits each individual gradient component to a fixed range. Another approach, clipping by norm, rescales the entire gradient vector when its overall size exceeds a chosen maximum, which keeps its direction but reduces its length. Clipping by norm is often preferred in deep learning because it maintains the relative balance between gradient components and helps prevent a single high-loss batch, such as in language model training, from causing overly large parameter updates. Choosing a gradient clipping threshold usually requires empirical tuning. If the threshold is too low, it can block useful updates and slow learning, causing underfitting, while a threshold that is too high may rarely activate and fail to prevent instability. A common strategy is to start with a moderate value, watch metrics such as the loss curve, and adjust based on how training behaves. In practical applications like recommendation systems and reinforcement learning, gradient clipping often helps stabilize training, especially when used together with an appropriate learning rate and normalization layers. Python code, gradient clipping basics. This script demonstrates basic gradient clipping by comparing model training with and without it. It uses a very small synthetic regression dataset to keep the examples simple. By observing the two training runs, you can see how gradient clipping affects the stability and behavior of the learning process. The line with the exclamation mark is a command to install TensorFlow version 2.20.0, which helps ensure the code runs with the correct version for compatibility and reproducibility. In the script, This line is commented out, so it does not actually run. It serves more as a suggestion or reminder of which version to use. If you needed to install that version, you would remove the comment and execute the command. We begin by importing a few key libraries needed for our work. The operating system library lets us manage files and directories. The random library allows us to generate random numbers in a controlled way so experiments can be reproduced. We then import NumPy for efficient numerical computations with arrays. Finally, we bring in TensorFlow, which we will use to build and train machine learning models while demonstrating gradient clipping. To make our code give the same results every time it runs, we set a fixed seed value, such as 42, for all the random number generators we use. We apply this seed to Python's random module, to the random functions in NumPy, and to TensorFlow's random number generator. Using the same seed across these libraries ensures that any random numbers or random operations are repeated exactly in each run. This consistency is essential for reproducibility, especially when debugging or comparing different runs of an experiment. This line displays the version of TensorFlow that is currently in use. It provides a quick check that the correct version of the library is installed and accessible to your script. Confirming the version helps ensure compatibility and that TensorFlow's features and functions behave as expected. The code first asks TensorFlow for a list of physical devices of type GPU to see if a graphics processor is available. If at least one GPU is found, it sets the device type to GPU, so computations will run there. If no GPUs are detected, it falls back to using the CPU instead. This lets the program automatically adapt to the available hardware and use the faster GPU when possible. This code prints a message telling you whether TensorFlow will run its operations on a GPU or on the CPU. It does this by checking if any physical GPUs are available on the system. If at least one GPU is found, it reports that the device type is GPU. Otherwise, it reports CPU. Knowing this helps you understand what computational resources are being used, which is important when you care about performance. We create a small synthetic regression dataset by first choosing 256 samples. The input values are drawn from a uniform distribution between -2 and 2 and arranged as a single column. We then generate noise from a normal distribution with mean 0 and standard deviation 0.5, matching the shape of the inputs. Finally, we compute the target values by taking 3 times each input, adding 2, and then adding the noise, which produces a simple linear relationship with some randomness. The code first turns the input data into a TensorFlow dataset, so it can use TensorFlow's efficient data pipeline during training. It then randomly shuffles the samples using a buffer the size of the dataset, and uses a fixed random seed so the order is reproducible each time the code runs. Finally, it groups the data into batches of 32 samples, which allows the model to process multiple examples at once and improves training efficiency. We define a helper function that builds and compiles a neural network model using the Keras interface in TensorFlow. The model takes a single input feature, passes it through 2 dense layers with 32 units and ReLU activation, and then outputs a single value through a final dense layer. Inside the function, we choose the optimizer settings based on whether gradient clipping is requested. If clipping is enabled, we use stochastic gradient descent with a learning rate of 1 and a clip norm of 1 to limit gradient size. Otherwise, we use the same optimizer without clipping. The model is then compiled with this optimizer, mean squared error as the loss, and mean absolute error as a metric, and the compiled model is returned ready for training. This script shows how gradient clipping affects training a simple neural network in TensorFlow. It uses a small synthetic regression task where the target is a noisy linear function of the input and trains two models with a high learning rate, one with gradient clipping and one without. Both use stochastic gradient descent, and their performance is compared using the final mean squared error. The model with gradient clipping usually trains more stably and ends with a lower error, illustrating that clipping can help stabilize updates when learning rates are large. Stable learning rate choices. Choosing the right learning rate is essential when training deep models because it controls how strongly the optimizer updates the parameters based on the gradients. If the learning rate is too high, the loss can jump around or even diverge, and if it is too low, training becomes very slow or may stop improving. Ideally, the learning rate should let the loss decrease smoothly with only small fluctuations. In this way, it helps the model move across the loss surface efficiently without losing stability. To keep training stable, it is better to use an adaptive learning rate instead of a fixed one. Begin with a cautious rate and adjust it based on how the loss and gradients change. If the loss is shrinking too slowly, you can raise the rate. But if you see sudden jumps or invalid values, lower it. Gradually reducing the learning rate over time helps the model fine-tune its parameters, especially with noisy data, such as in speech recognition, and prevents destabilizing updates. When tuning a model, always consider how the learning rate interacts with batch size, optimizer, and regularization. Larger batches usually support higher learning rates because gradients are more stable, while smaller batches often require lower rates to avoid unstable training. Different optimizers handle gradients differently, so a learning rate that works for one may fail for another, and it should be retuned whenever you change the optimizer, batch size, or architecture. In high-stakes areas like medical imaging, careful learning rate tuning with pilot runs and automated sweeps is essential to avoid unstable behavior and unreliable predictions. This script shows how different learning rates affect training a simple regression model in TensorFlow. It creates a noisy linear dataset, builds a basic neural network, and then trains two identical models, one with a small, stable learning rate and one with a very large, unstable learning rate. Over 15 epochs, it records the loss for each model without printing intermediate output. The model with the stable learning rate gradually reduces its loss, indicating effective learning, while the model with the unstable learning rate tends to show erratic or increasing loss. The final losses for both models are printed side by side, so you can clearly compare their behavior across epochs. In this lecture, you learn to enable and configure mixed precision training in TensorFlow 2.20.0 to leverage modern GPUs and TPUs. Use TensorFlow profiling tools to identify performance bottlenecks in models and input pipelines. And diagnose and mitigate common numerical and stability issues such as NaNs and exploding gradients. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.